think it was not having B.
Oh, B also you have problem. Oh, okay, yeah, B is probably something that yeah, we should totally focus on B. Oh, this kind of thing, like conservation momentum is, I remember the first time I saw this, is in a choosing question. It's a small, but I still quite surprised. Yeah. Suddenly you have another one horizontally. Conservation momentum still happen. Is that okay?
Mm-hmm. Yeah.
And some people say, isn't that there's a force vertically? Yes, vertically conservation of momentum doesn't really happen. But horizontally, there is no force, right? Horizontally, there is no outside force, right?
Mm-hmm.
And then E.
Would the answer to part C be different if the clay laid on the block? C be different if the clay had landed on the block when it was at a different position. Period. No, because the equation for the period still be the same.
Yeah. So K is still the same, right?
Yeah.
And mass is still the same, right?
Yeah.
It's still M plus M. So that
Yeah.
doesn't change. And F. What would the
F.
answer of D be different?
D would be yeah. Wait. Yes, right? That is
You can make an example about this.
if the clay had landed on the block is in a different position. Yeah. Oh wait, yeah, because like if you put like more mass on it, then it has to move more mass and it'll be like smaller. That's for the amplitude. Like if I had like the moving spring and I put like a heavy thing on top, then it like it might still move, but it'd be like a lot less.
Wait, can you draw it, Lildo?
Like
Is it okay
wait,
to draw?
if you consider it like uh wait, was that different in position? Okay, when it's like here, it uses like half of its kinetic energy, right? And then if you put the mass on it, um, if you put like a mass on it here, this would have like a different amount of like movement if instead of us like if it was like if it was all the way here. This is mostly like potential energy now, this on top. And
Oh, you're talking
then
about this, right?
yeah,
XXA? Yeah, yeah. So there's no speed at that time, right?
yeah.
Okay. If it's no speed,
Mm-hmm.
which means what we do before, well, let me see. It's basically kind of like m times 0 plus m plus m and v prime. So v prime is still 0, right?
Yeah.
So at that time, I guess there's no change. Does that make sense? Because you're not adding anything new, right? You're not adding any new energy, right? Because we say K prime is a little bit different plus US. But this one, if this one is nothing, and US is going to be, well, the total, well, before, right? And it's 1 over 2 Ka prime squared, and so A would be the same, right?
Mm-hmm.
So which means F is yes, right?
Yeah.
If we change it, for example, X equals to A, and the result is different, right?
Yeah.
So no other questions?
No.
Yeah, so this kind of A, 1 over 2A, A, and 0, they're pretty popular when they talk about energy or displacement. Does that make sense? Because it's the conservation of energy anyway, but using 1 over 2A or A or 0, it's easier. So we normally use them as examples. Unless it's, unless it's required in another way. Now let's doing the, we're doing circular motion a little bit before. And now let's talk about a little bit more why it can circle. So torque and rotational motion. Ever heard angular displacement and translational displacement?
No.
Translational displacement basically is the displacement we do before. For example, there's a block of car, so here's his displacement. Okay? Or even if you can fly, and this is your displacement.
Oh, is angular displacement around the circle?
Yeah, that's it around the circle. So basically, well, if it's a circle, what exactly is the displacement? It's just the, it's kind of like just the dot theta. Does that make sense?
Oh, for angular displacement?
Yeah, like how far you go about there.
Okay.
Does it make sense? It's just the dot theta, basically. If I go from here and I make a theta, and so this dot theta basically is angular displacement. Does that make sense?
Mm-hmm.
Of course, like the trigonometry, we do it normally anti-clockwise. So there is some relationship. This is we learn in the geometry, right? This is arc length, basically. Okay?
Oh, arc length over
Arc length is theta r, right? Remember? Okay, so L equals to theta r, right?
Oh yeah. Oh yeah.
They just use S. It's the same thing, right? They just want to know this, the relationship between them.
Yeah.
So now we have displacements dot theta for like a angular displacement. So it's only natural that we compare a little bit, right? This is linear velocity, which we also call translational velocity. Same thing.
Mm-hmm.
Or just velocity, as we say before. And now we say this is the omega equals to dot theta over dot t. Does that make sense? Because this is displacement for angle.
Mm-hmm.
And so this is the union before. Now it's the reading over a second, right? is the angular speed, right? Because you can say degree, but normally we use radian, right? And also it's good for calculation because this is easier calculation other than degree. So in this part, we like to use radian, no degree anymore. Does that make sense? If you see degree, you change it because in this equation, we specifically ask this one is radian, right?
Mm-hmm.
Yeah, so that's why it's radian over second. Or sometimes you can see that it's rotation, revolution per minute or per second. That means this is also used. Like for 1 minute, it rotates or it like 100 rotation or 100 revolution. Is this making sense to you?
Yeah.
Yeah. You see this before, right? V equals to omega r. Have you seen this before?
V equals omega r. Omega is angular velocity.
Yeah.
And what's a V is like linear velocity.
Yeah. Yeah, let me prove that a little bit. So because let's just say r times omega is delta theta over delta t, right?
Mhm.
R times delta theta, isn't that arc length s over t, right? S over t isn't that velocity, right? Does that make sense? R times delta theta is the arc length. Arc length times the t, for example, this is the arc length. This is the arc length times the t that you use to travel from here to here. Isn't that translational velocity or linear velocity, right? Does that make sense?
Mm-hmm.
So this is v equals to r omega. We also use this. Well, if they say they want to say it's a vector form, vector v equals to r times vector omega. Well, sure. You don't like vector, so we all use vector, and it packed with the data calculation. In here, and also it starts with in here, right? It starts in here.
Okay. Yeah.
Angular acceleration. We have, well, before we have a equals to delta v over delta t, right? This is acceleration before, right? Since we know delta v can correspond to delta omega, so v corresponds to omega. So delta v is basically delta omega, right?
Mm-hmm.
Yeah, so now I have, well, delta t is the same. Delta omega over delta t. We like to talk about this rotation because let's say got like circling curves rotation a lot in this. We use a lot about this. And also you learn that waves, right? We also need a lot of waves this everywhere. All kind of radiation. So because, remember we have big five, right? If everything kind of similar, hopefully the big five is similar. This is linear, right? It's basically the average velocity. Of course, this is a requirement. It's the uniform acceleration. So this, and this is also uniform acceleration for rotation, I guess. So this is initial omega, initial angular velocity. This is the final angular velocity, right? And so this is final velocity equals to initial velocity plus the et. And then this one is this. This one is basically alpha. Well, although sometimes they read A, but it's actually alpha, just to be a little bit different. So this one is also very similar to this one. You just change basically everything about V, change everything about omega, right? And X into theta, basically, right?
Yeah.
Does that make sense? So this is the initial angular velocity, and this is the final angular velocity. And this minus this is basically delta x or delta theta for this one. Oh, this is the one that sometimes it's difficult to remember, but easier for some calculation. Let's do example one.
One radian per second in 10 seconds. What is the angular acceleration? What is its linear rotation? Zero 0.4 radians per second. In 10 seconds. Oh, we can use the uh 1/2. Wait, it accelerates to 0. Wait. One half. Angular acceleration. Angular acceleration is alpha, right?
Yep.
Okay. So V equals so 0.4 radians per second equals 0 plus a 10 0.4.
Yeah. Radian per second square, right?
Yeah. What is it? The linear rotation? Is this asking for like x?
Linear. What is linear?
It says linear rotation.
If it
I
is
think
3 meter,
so like it's
so
like
like
that.
this, yes.
Three? Oh, and then it's asking for like the arc length.
Well, I think it's asking for linear acceleration. You should read this. What is angular acceleration? And then it's what is its linear? Which means linear acceleration. Wow, I think it's a typo. It's right. Acceleration.
Theta
One is asking angular, one is asking linear. The linear acceleration.
x equals theta r, right? It's like linear.
Not like exactly like the linear acceleration. So which means A basically he's asking.
A is delta V over
Wait, yeah,
delta V
delta
over
V over delta T.
uh velocity. Um, wait, isn't x equal to theta r?
Well, it's R time delta omega. Does that make sense there?
Delta omega.
No, not this one, and this one. Because delta V, you can see that R, well, let's say omega minus R omega 0, right? Does that make sense? Because we have V equals to R omega, right?
R times omega.
Hmm.
Omega is...
So this is R can get out, and omega minus omega 0 over t, right? So this one isn't that angular acceleration, which is R alpha.
Or alpha.
That means
Wait.
because alpha is delta omega over delta t, right?
Oh, and we already found alpha.
Yeah, we already find alpha.
3.
You can just use 3 times that 0.04 thing, right?
Yeah.
There's kind of some deducing in here. So let's review what we can do in here. It's better to remember this. It's better to remember this. And also it's better to remember A equals to R alpha. Again?
Mm-hmm.
Now that's making sense, right? Okay. So that's example 1. Center of the mass. Well, let's skip this. Look at this. Not looking at it. So this is basically what he using here is this hammer. If you throw this hammer, you can see that although this goes up or down, right?
Mm-hmm.
This stick. And it seems like if you look at this as the center of the mass, it's actually in a parabola. Does that make sense?
Mm-hmm.
So which means somehow this hammer is simplified as a point if we can find the center of the mass, right?
Mm-hmm.
Does that make sense? So that's probably one of the reasons, for example, there's a little baby walking. When people start to walk, they thought I have to control everything in my parts, in my body. But actually, what we do eventually, by instinct and by experience, is what we do is only control the center of our mass. Does that make sense? This is one of the mysterious things in this universe. We don't really know why mass or just rely on one point almost. Does that make sense? So also for the circus people, sometimes they have a string, right? And they walk in there, right? This is talking about adults. And he's holding a stick in there, right? So what he does is also find your own center of the mass. Make sure your center of the mass is vertically upward above the string. So you'll be okay, right? So center of the mass happen to be very convenient for humans to live there. I mean, in the universe. Well, to be honest, it is not. Well, it's actually also right when you have to say, don't I have to control every part of my body and every little mass in my body? We have. Does that make sense? There are so many mass, so many gravity in there. Does that make sense? But somehow, this is all true. But this is all true is because if this is the center of the mass, I can also just control the center of the mass, then I can control the whole body. Does that make sense? Let's just say center of the mass mysteriously happened there. It's not wrong to say that I have to control every tiny molecules in my body. It's also right. But on the other hand, it's the same effect if you think about it in a general view that you can control as long as you control the center of your mass. So, and also where do we find? So in this geometry figure, which means regular size, and the density is constant. So the center of the shape is basically the center of the mass, right?
Mm-hmm.
So this is easy to think. How about this one? They also at the center, but it's actually not on the body, which is okay. Is that making sense?
Yeah.
If this is like the magnet thing, so the center of the mass is actually in here. And if this is a little, what is this, tire? And so the center of the mass is in here. So some people say, should it be down here? Well, not exactly.
Mm-hmm.
And if it's irregular, well, and they said most of the mass rise and the center of the mass will be close in there, right? It depends, right? Have you learned torque before? Oh, moment, same thing.
No. Torque is like rotational force, right?
Yeah, well, it's a rotational effect, you can say, or it's a turning effect. Some will call it. So for example, if this is the door, this is the same location that I push. If I use greater force, I have a greater effect, right? That's why we also call it turning effect. What's affecting the turning effect? I guess the force, in this case, force is going to influence my turning effect, right? Or torque. And what else is affecting the turning effect?
Where you put the force?
Yeah, let's do that. So where is here, right? Same 100 Newton. If I push this door, this one will have less effect, right? So that's why we always push in here, right? When you push a door, you don't want to push in here, right? That'll be difficult to push, right?
Mm-hmm.
So wait, how far is this contact with this, all I can say is axis, right? Or pivot, right? It's kind of important. And if we do more about this, for example, if it is still the same location, it's the same location. What if I have different directions? And this is 100 Newton. And here, all 100 Newton. All same location. The end of the stick. I mean, the door. You can imagine, let's say this, the extreme one. How about this one? Can this one open the door?
No.
You can't, right? You don't make a circle, right? You don't make a rotation here, right? So the more we do, we find this is the three things that's connect with it. Well, of course, they have other factors at a time, but it turns out all the other factors doesn't really influence the turning effect. So eventually, it's the force magnitude and the angle theta, and also radius. Does that make sense?
Mm-hmm.
And the more we see it, more force. You can imagine it's more torque, right?
Mm-hmm.
And more radius is more torque. Well, say more theta, also more torque. Well, eventually it's not exactly more. This one is not exactly true. It turns out it's more what sine theta increase than it's proportional to torque. We actually use not exactly T because it's confused with its attention. It's something like this. We call it torque. I mean, it's a Greek letter. Little circle in here and a little this. So eventually it's torque equals to F R sine theta. What is R sine theta is something that the scientists discovered. It's something like this. For example, it's basically this. So if this is R, see this is R. Say this is R. And sine theta, if this is theta, then this is theta, right? So sine theta, R times sine theta is this one. Does that make sense?
Yeah.
Yeah. Eventually, it's not how far, it's how far from the pivot to the, well, it's basically is the distance from the pivot, or you can say perpendicular distance. I mean, perpendicular distance from the pivot to the action line of the force. So this one. Does that make sense?
Mm-hmm.
So what is this one? This basically is r sine theta. So that's why it's r sine theta proportional to torque. And r sine also force proportional to torque. So torque equals to F r sine theta is the final turning effect or torque that we talk about. Does that make sense?
Mm-hmm.
Seesaw also works like that too, right? See? Normally we want a seesaw in here, the higher weight, right? You don't want to sit in here, right? And also you don't want to push it. When you push it, when you, for example, you play with a baby, you don't want to sit there because, you know, you're too much force. So you want to push it, you don't want to push in that direction. You don't want to push in this direction. Maybe less effect. Does that make sense?
Mm-hmm.
So this eventually is our torque effect. But this is going to make rotation happen, right?
Mm-hmm.
Or torque is FL2. So L is just the perpendicular distance from the pivot to the action line of the force. Same thing. Torque FR sine theta. They are basically the same. Does that make sense? Because in before before they actually have like F or L or R and or like L like R or theta or sine theta. The test or some others. Eventually this come up with a pattern. How about two? Example two.
40 Newton. Wrote that line around radius 5. What's it asking for?
Torque of this force.
Is 40 Newton, 5 centimeters. It's just proportional to the force of the straight. This is 5. Oh, it's just 40 times 5.
Yeah. I mean 40 times 0.05, right?
Oh, right. That's it's 2. 2.
Yeah. What's the unit?
Newton meters.
Yeah. So which means this is the center, right? This is the pivot, kind of. And so this is the force. So you can say this is the FL's L, right? Perpendicular distance from the pivot to the action line of the force. Yeah. And also you can say sine theta is basically 90 degrees, so you don't have to think about that. For me, I basically which one I like? I like this one. So I call this L is perpendicular distance from the pivot to the action line of the force. And this is my R sine theta is my perpendicular distance. So that's how I remember. 3.
At torque on the cylinder. It'd be 100 0. Wait, 0.12 minus 80 times 0.08. And equals 12 minus 5.6.
Yeah, and it's positive, right? So you know this
Yeah.
is anti-clockwise is positive, right?
Yeah.
And so this clockwise is negative, right? Yeah. It is making sense in like a real like life phenomenon, right? Well, you use this one a little bit more, so of course this one is actually oppositing its resistance to the other direction, or to the other effect, you can say. Equilibrium. Before we say equilibrium, which means translation or linear, right?
Mm-hmm.
At that time, because Newton's first law works, so F net is 0, right?
Mm-hmm.
Now we also have rotational, which means torr is 0. Does that make sense?
Wait. Oh, yeah.
Yeah, which means if you have no rotational effect, then it must be torr net is 0, which means basically something like this. If what you provide in this and what you provide in this, they actually met each other when positive and negative, the balance. So there is no rotational effect. There is no rotation. It's basically rotational equilibrium, right?
Mm-hmm. Yeah.
And when that happens, you basically can say torque 1 plus torque 2 and, is 0, right? Torque net is 0, right? Does that make sense?
Yeah.
As long as you basically at a rest, that will happen. So let's do example 4. It's a little tricky, this one.
The uniform bar mass and length along extends. Okay. The system, the wall has friction. The tension in the wire. So this has force pulling down. It's at the like with this one also has force down, but this one has to be pointed back up, and then there's force here.
I remember in momentum, well, just wait a second. In momentum, you remember we have, we have conservation of momentum, we also say x coordinate, y coordinate, momentum conservation always also happens, right?
Mm-hmm.
So in that case, which means if we have component, for example, torque x1 plus torque 2x plus torque 3x, they're all 0. And torque 1y plus torque 2y plus torque 3y, all 0. Does that make sense? So this indicates another 2 of this too. Does that make sense?
Uh-huh.
In different directions. I don't like to use this method for this question, but I guess it's okay. When you learn that one, not bad. So we might want to use that one.
So, and from this one, so this point here would be the where it's rotating, right?
Yeah.
So then,
And also this one, we also rotate too.
yeah, and then there's tension in the
We also consider like this 2M our system, right? Yeah, that the
yeah.
tension is something else. So. Oh yeah, we have a normal force from the wall, right?
Mhm.
And so there's a friction.
Tremendous tension in the wire. The tension is these two, right? In the wire, it's just these two, right?
Yeah, this is the gravity, right? This one is the gravity. So there must be like a friction kind of thing in here, right? Otherwise we would just fall, right?
Yeah.
Why don't you fall? Because there's friction going upward.
So these uh, uh, so oh okay. So M L plus M 1/2 L.
When you say M, you mean mg, right?
Oh yeah. Yeah. G G these two have to equal and then if you add the wall or uh like T wall this all equals 0
Yeah, you mean
minus
torque.
T. Yeah.
mgl plus 1 over 2
L
mgl means mg. Oh, let me think.
T T towards the
Yeah,
wall
1 over 2 L.
and then minus the torque of the wall, so negative torque from the wall equals so M is 8 kilograms and 12 grams. Um, 12 times L times 10 plus 1 plus 6.
Oh, you don't have to go all the
Wait.
way in
Oh, okay.
because we might simplify later. So basically, what do you say? Torque equals to, well, basically negative, or you say that one is negative, then it's the positive. MGL plus 1 over 2 MGL, right?
Mm-hmm.
And also because the tension is in here, right?
Yeah.
And this part is 1 over 2L, right?
Mm-hmm.
So basically it's F tension times this is sine. If this is a perpendicular distance L, right? So this is 1 L over 2 times sine 55 degree, is it? Is this one?
Mm-hmm.
So this one would be L over 2 times sine 55 degree, right? Equals to all this, right?
Mm-hmm.
Does that make sense?
Yeah.
I think we probably have it. Let me see. If that's the case, L and L can be all simplified. We all have L, right? L and L can be all simplified. So I can find FT, I think. So FT is gonna be, let's time it 2, because there's 2 in here. Time it 2 in here. So here it'll be a 2, and then here it'll be 1. So it's 2 mg and plus mg, right?
Mm-hmm.
And over sine 55 degree, right? Does that make sense?
Mm-hmm.
Is that tension? Yes, I think that's the tension. And also, I want to say something about why friction does not rotate. Does that make sense?
Oh, yeah.
Because they go through the pivot. Yeah, for example, let's use seesaws. So if you push it here, yeah, oh, okay, right? But if you push it here, or you push it in here, it's not working at all, right? I mean, all this 3. Does that make sense?
Mm-hmm.
It's not working, right? As long as you go through the pivot, there is no FL. Perpendicular distance from the pivot to that one is always 0, right? If your action line from the force is going through the pivot, so there is no rotation. Does that make sense?
Mm-hmm.
So that's why this force does not have any rotational effect, including the normal force in here, right?
Mm-hmm.
So although they have forces on the system, but they don't really have effect. They don't have turning effect. So now I can just find my tension, right? Is that making sense?
Mm-hmm.
So that's my tension, right?
Yeah. Negative sine of 55. Yeah. Yeah.
I can just substitute and I got my tension, right?
Mm-hmm.
How do you find the strength of the force exerted on the bar by the wall?
Um, uh, um, force into the wall from the wall would be
We're trying everything about a torque right now, right? Now maybe it's time to think about linear, which means not only the sigma torque should be 0 or torque net should be 0. This is what we just did it. I can also say sigma f is 0. Does that make sense? As long as they are in equilibrium,
mm-hmm.
right? All the forces must be balanced too, right? Otherwise, you can't really make the linear. So how do I find sigma f is 0? Now I have to use all this friction and also normal and tension and then force and then gravity force. They should all balanced. All 1, 2, 3, 4, 5. 5 forces. I mean, and think about them as a point. That system, but I can say this system have 1, 2, 3, 4, 5, 5 forces, right?
Mm-hmm.
So eventually, these 5 forces have to be. I can consider them as a point. All these 5 forces have to be balanced, right? Does that make sense?
Mm-hmm.
So how do I make that happening? How do I make that happen?
Everything adds up to 0. You and is oh, and then you have gravity too.
Can find all the components horizontally and all the components vertically to be 0 if we add together, right?
Mm-hmm.
But just, well, in that case, all this 4 is in XY system anyway. Only you have to find a component of the tension, I guess, right?
Yeah.
So can you find the, well, all the forces?
That's the that'd be G and then mg and the gravity. Normal force from the wall and tension, which would be this component and then this component. This is this is 1/2 of L sine theta. L sine theta.
Wait, are you using L?
Yeah, wait, you can't use L.
What do we think? We already use L, which means when we talk about a torque net to be 0, I mean sigma torque to be 0, we already use that torque already, which is the new knowledge that we learned. We should use the old knowledge, all the forces, sigma F to be 0 to solve the force. Let's just pretend we already have F tension.
Mm-hmm.
So because the F sigma torque to be 0, we already find F is like a, I can't remember, F of 2 mg plus mg over sine 55 degree, right? We can totally get this, right?
Yeah.
And because of this, I can also think about horizontally how force is balanced. See, this is the tension. I can find horizontal component of my tension, which is Ft time cos 55 degree, right?
Mm-hmm.
Ft cos 55 degree. And it must balance. This is basically this one. Must balance with the normal force, right?
Yeah.
F normal. Does that make sense?
Yeah.
So horizontally balanced, right?
Yeah.
Does that make sense? So this is my equation 1. How about vertically?
Vertically is mg plus mg, the two
Yeah,
mg's, and then yeah,
mg plus mg
and
equals
then
to,
um has to equal the tension pulling it up, the vertical component of the tension.
yeah, and also there's something else here too. Friction, because they mentioned friction,
Oh,
right?
friction. Yeah.
So friction. So that'll be F friction plus F tension time, what's this? Vertically, I guess it's this, right? Sine 55 degree, right?
Mm-hmm.
Does that make sense? This
Mm-hmm.
geometry thing is tricky in the beginning, so you have to basically draw it very carefully. And before I actually draw this one out. See, this is F tension, and this is 55 degree, and this is my FTX, this is FTY, right? And then I use trigonometry totally deduce all the way. So this is basically how I get this one, right? So with this one, I can get a friction, right?
Yeah.
Can I get a friction? Mm.
Friction. Oh, friction you need the normal. Yeah. Normal force, right?
Oh, you mean friction?
Yeah.
Oh, in this friction, we don't use normal force because it's static friction. We can't really use normal force,
Oh,
right?
yeah.
And also, we can solve it in this equation. In this equation, everything else we know, right? Only friction we don't know. I can use this equation too to find my friction, right?
Yeah.
You want to do this one?
Uh, you have to simplify everything.
Yeah, a lot of simplifying to do.
M plus M is 20
20.
times 10, so 200 equals, is that FT? FT.
I have tension. I have friction.
Oh, that's F friction plus F T.
Oh, Ft is 2 mg plus mg over
9.
sine 35 degree.
Okay.
Oh, good thing that
And
sine
then those
get
line
cancelled out,
cancel.
get simplified. Great.
So 2 times
Oh, that's 2 mg. That's plus
A
mg. Oh, I guess it's mg
280
only. That's great.
plus mg, which is 120. 60 plus 120. That's 280. So that means F from the friction is negative 80.
Wait, friction is negative 80? I think.
Yeah.
I think friction is 120.
Mm,
See, don't you have m plus mg on this? mg and mg. And then you have 2 mg and mg on this side, right? Everything is canceled out. There's only one is negative mg
oh,
equals to the F friction, right?
yeah. Oh, so
It's
then, okay,
calculated.
yeah, it's 120.
It's 120, right? What about the normal force?
That's friction. Normal force would be
And normal force is according to this. F normal equals to Ft times cosine 55 degree.
looks like 55. Um, then you have to just multiply everything. So,
Yeah, so just time cos 45 degree, which means this is cot 55 degree, right? When you read anything.
yeah.
So basically it's 2 mg plus mg times cot 55 degree, right?
Yeah.
So one can help me to find my F normal. So after, for example, already find F friction, already find F normal, then how do you answer the second one? The strength of the force exerted on the bar by the wall.
It's just the normal. That's only in the horizontal direction, right? For the force to be
Yeah, so this one is 120. And this one, let's just say F normal. We already find it. It's basically this one. So how do you answer this one? The strength of the force exerted by the bar on the bar by the wall. Which one of this is the force they ask? Or what is the force they ask? The strength of the force exerted on the bar by the wall.
Force normal? Is it just force
So
normal?
friction is also a force from the
Oh,
wall, right? So
so
both of
it's
them actually is what they want. Does that mean? They want
Yeah.
f normal. They also want this. So you just have to add these two together. Does that make any sense?
Yeah.
That's tricky us in this part. We normally saying the bar like the wall gives some thing a force is normally the normal force, right? But in this case, it also includes the friction, right? Friction also
Yeah.
comes from the wall, right?
Yeah.
So that's why I have used Pythagoras, right? If I
Yeah.
use vector like a triangle, so this one and this one. So just square root 120 square plus well plus this fn square, right? Does that make
Yeah.
sense?
Yeah.
You gotta be careful. This is kind of popular in AP or in A level. They all like to ask this question, and this is a pretty common thing in construction world, also in the bathroom. That this is called like a triangle shell thing, right?
Mm-hmm.
Just remember sigma f. What do you want to remember about this question? Sigma f equals to 0. And
Yeah.
sigma torque equals to 0. Including this one is sigma fx to be 0 and sigma fy to be 0. And this goes to, torque x to be 0 or sigma torque y to be 0. You can also use this, but I didn't really use it because it's, well, they don't really have a lot of torque there. They only have 3 forces giving a torque in this one, right?
Mm-hmm.
Does that make sense?
Mm-hmm.
Okay.
Yeah.
Oh, let's see. The result is 250. So
Mm-hmm.
basically 250. Let's estimate a little bit. So this two, eventually 250 is not a very large force. I guess it's making sense. Normally 1 Newton is 1 apple's weight. So 250, not that much, but it's okay. It can be provided by the wall. Well, I guess I have to leave this one. Newton. Well, the homework is just all the questions that we did in the class. Especially with 4. So that's an example 4. Okay. Yeah, it's not that easy, like example 4. And also the one that we did for response, that one, you probably should also do it. You can go on with the other one, but it's a little difficult. Also because we skip little always, and they provide it in the test, so well, we don't really get into too many details until later. Do you have other questions?
No.
Let's just see all the formulas that we learned. Because I have to explain rotation inertia, which is a little tricky, especially to skip a little more than formula. So big 5 is all included in rotational. Does that make sense? This.
Mm-hmm.
And all the, well, also something in here. It's a little before big 5. It also works too. You can try to do the exercise after it, but some of it you can't. It's a little, we have to use what we learned before. Some of it you can do. So I would just also include the one that's for this chapter, but you have to know some of them you can't do. Does that make sense?
Mm-hmm.
Okay. And the torque, I remember this one. What's this L called?
L. L is
Perpendicular distance. Remember, it's perpendicular distance from the pivot to the action line of the force. See? So this. So for example, if this is the case, you have to find the action line and then make a perpendicular distance. So this one is the perpendicular distance. Does that make sense?
yeah.
And or also you can remember this. So this obviously this r is not perpendicular distance. R times sine theta is the perpendicular distance from the pivot to the action line. Okay, so that's it for today.
Okay.
Have a good day. Mm-hmm.